Let's continue to capacitors in an AC circuit. So for this subtopic, we are going to consider only one capacitor placed or connected to AC generator within a closed circuit. So we also call this kind of circuit is purely capacitive circuit. Alright, so what will happen? Okay, please recall that capacitor actually parallel plate of conductor placed parallel to each other, and between them there is filler, or it could be vacuum or air or any kind of filler that going to cause charges being accumulated or collected within the plates of the capacitor. So the purpose of capacitor actually to accumulate or store charge, or electric energy in terms of storing of charges. Alright, which is in opposite to the resistor. Resistor, the purpose of it is to reduce or to limit the number of electron that can pass through within a circuit. Alright, so for capacitor, to store charge, or in other words, store electric energy within the plates of it. Alright, so based on that behavior, now, the way how the current and voltage, react within the capacitor will be varied compared to resistor. So if you see here, the voltage reach its maximum value 90 degree after the current reaches its maximum value. So the voltage, known as or called as lags the current by 90 degree. If you refer to this graph, you see here, this is your current, which is in terms of cost function for one complete cycle. And here you have sine function for one complete cycle. And to change between from cos to sin, it's possible to convert it. It's just like we have to add part of it, isn't it? Then it becomes sin function as well, right? So it means that the I, the I leads, the movement of the I leads or leading the voltage within capacitor, right? Why does this happen in terms of understanding or simple method? Simple understanding saying that whenever current flow, let's say from the generator entering the capacitor will now not allowing the current to be completed until the plates is fully charged. So first thing first, current is allowed to enter, but then the purpose of it is to charge itself, to accumulate the charges on the plates of the capacitor. So if you measure the voltage across the resistor, let's say you put a voltmeter, you want to measure, you put voltmeter here. Alright, you want to measure the value of delta VC, like this one, alright, across the capacitor. You cannot have the reading until the parallel plates being fully charged firstly. So to have it fully charged, the current is allowed to pass through, but not the reading of the delta V yet. So in simple, it means that the capacitor, whenever the current flowing into it, it will allow the current to complete the circuit, to flow within the complete circuit whenever itself already fully charged. So you cannot have the reading of voltage drop across the capacitor until the plates are fully charged. Right? That is why the current is leading the voltage by 90 degree, quarter of a complete cycle. Or we can also put it as voltage, voltage lags the current by 90 degree. Or in other term, we can put it, current leads voltage, okay, by 90 degree. This one and this one is the same statement actually, right? Either one, right? So then capacitive reactance, the moment, okay, the moment current flow within the capacitor, there is impeding effect of the capacitor on the current. What does that mean? Okay, it means that, okay, the moment current try to flow into the capacitor going to say, no, you are not allowed. Please charge me up, okay, until I'm fully charged. Then you may pass me through, isn't it? So that kind of effect actually, we call it impeding effect, a kind of resistance, isn't it? It's make it hard for the current to flow. So kind of resistance. So we call it impeding effect of a capacitor on the current in AC circuit is called the capacitive reactance. How big, how hard for the current to flow, we put it as capacitive reactance, the reaction of the capacitor in simple, right? So the formula is this one, XC equivalent to 1 over 2 pi F C. So if you compare this to this one, omega C, because 2 pi F is also equivalent to omega. Alright, and the unit is radian. What is omega? It's angular frequency. Right? So the unit of it is radian per second. So the Ohm's law within the capacitive, purely capacitive circuit, or we call it capacitive reactance, the XC, okay, is also applicable. But now, okay, the term is in term of delta V across capacitor, okay, is, okay, in term of RMS is equivalent to I across the circuit in term of RMS times with the impeding effect, or we call it capacitive reactance of the capacitor. Okay, so if we compare this to the Ohm's law, the normal Ohm's law, delta V equivalent to IR, okay, previously, okay, so this one has a unit of, the XC has the unit of ohm, right? Because it's a, how big, is measure how big, how trouble, okay, for the current to pass through the capacitor. Okay, that is capacitive reactance, right? Where the XC must be determined by using this formula. Goes the same for the delta V maximum across the capacitor. Okay, so delta V across the capacitor in terms of maximum value is equivalent to I maximum flowing within the circuit times the capacitive reactance of the capacitor. Okay, so the unit of the delta VC RMS is volt. The unit for delta VC maximum is volt as well. Right, but if you want to determine the XC, make sure the F must be in hertz or per second. Okay, must be in SI unit. To cancel out the unit with the 2 pi here, because by right, okay, it's equals to omega. 2 pi F is equals to omega. Right. So let's take a look on question number 12. Right. AC generator delivers an AC voltage of the form delta V equivalent to 98 volt sine k80 pi to a capacitor. The maximum current in the circuit is 0.5 ampere. find A, the RMS voltage of the generator, B, frequency of the generator, C, RMS current, D, reactance, and E, value of the capacitance. So, from this equation, we know that here is some value of, this is actually the value of delta V max, isn't it? Right, then 80 pi here, this is actually the value of what? The omega, which is equivalent to 2 pi f. Right, so to solve part A, it's requesting for RMS voltage of the generator. For part A, right, for part A, delta V across capacitor for in term of maximum equivalent to 98 volt. Therefore, okay, delta V across the capacitor in term of RMS equivalent to 98, the delta VC max just now, divided by square root 2 or set 2, which is equivalent to 69.3 volt. Alright, next one for part B, frequency of the generator. So based on this information, right, so we already have for part B, omega equivalent to 2 pi f. Okay, so f is equivalent to omega divided by 2 pi. So our omega is 80 pi divided by the 2 pi, which gives you the answer is 40 hertz. Right, and then C, RMS current. For RMS current, we may use the information of this one. Maximum current is this value. So for part C, I RMS, okay, equivalent to I max, okay, I max over square root 2, which is 0.5 divided by square root 2, which give you 0.354 ampere. And then part D is requesting for reactance. Okay, reactance is XC for capacitor. Is delta V C. Okay, what we have here, you can use the maximum. Okay, if you use delta VC maximum, you have to use I maximum, V max divided by I max. Okay, which gives you, right, 98 divided by 0.5. The answer is 196 ohm. You may also use this one. Which is going to give you exactly the same answer. Okay, 0, your VRMS 69.3 over your IRMS 0.354 ampere. So you will get the same answer. And D settle. E, value of the capacitance. Value of the capacitance. So for E, right, for E, you want to know the C, right? So you have XC equivalent to 1 over omega C. So what is C is the things that we want to solve. 1 over omega XC, right? So 1 over omega is 80 pi just now, right? Your XC is 196 just now, right? Then you will finally get 2.03 10 to the power of negative 5 farad, right? Or simply 20.3 microfarad, the capacitance. Okay, so this is question number 12.